today we shall consider some problems, right, on context free grammars and also on finite state automata. Give a context free grammar to generate a power n, b power m, c power k, n m, k greater than or equal to 0 and k is equal to mod of n minus m. So, first of all you must realize that in a context free grammar like S goes to A S B and S goes to A B, there is a way to keep the number of A's equal to the number of B's. When you apply this rule, one A will be generated this side, one B will be generated that side. So, ultimately you get A power n, B power n. That is not possible with type 3 or right linear grammar. When you have rules of this form, there is no way to keep count on the number of A's and the number of B's. So, with type 3 to generate such a language having some equal number of A's and equal number of B's or number of A's twice the number of B's is not possible. You require a context free grammar for that, and it is not necessary to go to type 1 rules where on the left hand side you may have more than one symbol. It is also not necessary. For such things to generate equal number this side and equal number that side, you require only a linear grammar which is context free. You need not have to go to a higher level also. So, let us consider this one. Now, the possibility is you can split it into 2 possibilities or 3 possibilities, does not matter. So, n greater than m, I will split into 3. If n is greater than m, k is equal to n minus m or n is equal to m plus k. This is one possibility. The second possibility is n is equal to m. If n is equal to m, k is equal to 0. Third, instead of considering like that, you could have also split it into 2 like n greater than or equal to m, m greater than or equal to n, does not matter. That way also it is possible. Then another thing is m greater than n. In that case, k will be equal to m minus n and m will be equal to k plus n. Now, for each one of this you can give a context free grammar and the union of them will be the grammar which you require. So, you can have S goes to S1 where S is the start symbol and S1 will generate this portion, right. Then S goes to S2, S2 will generate this portion, S goes to S3 and S3 will generate this portion, right. So, second one is very easy. When n is equal to m, k is equal to 0. So, what do you get? You get 2 gives rise to the portion a power n, b power n, n greater than or equal to 0, right. This gives rise to this. And this you can very easily generate with S goes to ASB, S goes to epsilon. The first portion n is equal to m plus k. So, the strings will be of the form a power n, b power m, c power k, but n is m plus k. So, you can write it as actually a power m, a power k and so on, or rather a power k, a power m, a power k, a power m. So, S1 should generate that. Starting from S, you can go to S1 or S2 or S3. So, S2 generate, this is S2, okay. Second portion is generated by S2. So, S2 goes to A, S2 B, S2 goes to epsilon. Now, this one should be generated by S1. First, you can generate equal number of A's and C's by having the rule S1 goes to A S1 C. After generating equal number of A's and C's, you may go to a non-terminal A, because there is you can use unit productions, only in certain cases you have to avoid them. Now we are not asked to avoid them, so you can use as many as possible. S1 goes to A. After generating equal number of A's and C's, it goes to non-terminal A. Then from this you can generate equal number of A's and B's. So that will be A B, A goes to epsilon. So this portion will generate the first of this, and now we have to generate the third one. Third one, S3 has to generate that. M is equal to n plus k. So you can write it as A power n, B power m, C power k, but this m you can split. So it will be B power n, B power k, C power k. M is equal to k plus n. So you can split it like this. This is B. So you have equal number of A's and B's, then equal number of B's and C's. So this has to be generated by S3. So S3 you can make it go to CD, some non-terminals C and D. C is a non-terminal and D is also a non-terminal. Then C can generate A power n, B power n. C goes to A C B, C goes to epsilon. Because n, m, k are greater than or equal to 0, you can have epsilon in the language, and to have the possibility where this is 0 and this is also 0, you should have this. Then from D you can generate equal number of B's and D's. So that will be generated by B, D, C, D goes to epsilon. Instead of splitting into 3 portions like this, you could have split it into n greater than or equal to m, m greater than or equal to n. In that case, some of them will be generated in both, like A power n, B power n will be generated in both portions. That does not matter, right. So this is the solution for this. The main thing to understand is, when you want to generate something in this side and something in this side, use a linear rule. So that keeps count of something occurring on the left hand side and something occurring on the right hand side, and that is possible in type 2 grammars, linear, in fact linear grammars. It is not possible with type 3, and it is not necessary to go to type 2. When you have 3 of them, to make them 3 or 4 of them equal, like A power n, B power n, C power n, or A power n, B power n, C power n, D power n, something like that, when you want to keep equal number of 3 or more things, then you require type 1 rules. Now how many derivation can you draw for A power 4, A power 5, A power 6 in this grammar? We have considered this grammar earlier, and for A cubed there were 2 derivation trees. For A cubed there were 2 derivation trees. For A squared, for A there is only one derivation tree. For A squared 1, A cubed 2. Now how many derivation trees do we have for A power 4? Now the first step in the derivation tree will be like this. Now in this, from this S you can derive A cubed, and from this S you can derive A. This is one possibility. And from this S you can derive A squared, and from this S you can derive A squared. That is another possibility. From this S you can derive a and from this S you can derive a cubed. These are the three possibilities. Now, if you use this possibility, this a cubed itself can be generated in two ways. So, when you want to generate a cubed from this S and a from this S, of course, this can be generated in only one way. So, this gives rise to two derivation trees. And when you want to generate 2a squared from this S and 2a squared from this, I am sorry, when you want to generate a squared from this and a squared from this, there is only one possibility. So, that will give rise to one derivation tree. The same thing like this, when you want to generate 1a from here and 3a's from this S, this can be done in two ways. So, this will give rise to two derivation trees. So, totally for a power 4, you will have 5 derivation trees. Now, what about in a similar manner you have to calculate for a power 5 and a power 6, a power 5 and a power 6. Now, if you take a power 5, the first step of the derivation tree will be like this. Now, from this S you can derive a power 4 and from this S you can derive a, that is one possibility. Then from this S you can derive a cubed and from this you can derive a squared. From this S you can derive a squared and from this S you can derive a cubed and from this S you can derive a and from this S you can derive a power 4. Now, how many possibilities this will give rise to? A power 4 itself can be derived in 5 different ways. You can have this subtree itself can be drawn in 5 different ways, right. So, this will give rise to 5. A cubed can be drawn, for a cubed we can draw a subtree in 2 possible ways, a squared only one way. So, this will give rise to 2 different trees. Similarly, this will give rise to 2 different trees and this will give rise to, this can be derived in only one way, but the subtree here deriving a power 4, you can have 5 possibilities because we have already seen that. So, totally 14 different derivation trees you can have for a power 5. Now, coming to a power 6, the same argument, you can split it as a power 6a, a power 5, a power 5, a power 4, a squared, a cubed, a squared, a power 4, a power 5. The number of possibilities for this will be 14. For this also it is 14. For this a power 4 can be derived in 5 ways, a squared only one way. So, 5. This a cubed can be derived in 2 different ways. This a cubed can also be derived in 2 different ways. So, 2 into 2, 4 you can have. So, this will add up to 14 plus 14, 28, 38, 42. Now, for a power 7 obviously the number of trees will be very large, a power 8 still more and so on. As the length of the string increases, the number of derivation trees keeps on increasing. So, in this case you say that the degree of ambiguity is infinite. In this example, the degree of ambiguity is infinite, it keeps on increasing as the length of the string increases. Now, we will consider another language, a power n b power n c power k, n k greater than or equal to 1 union a power n b power k c power k n k greater than or equal to 1. We have seen that this is an inherently ambiguous language. Any grammar generating this will be ambiguous. Okay. The proof is difficult. I did not give you the proof is very lengthy, but this has been proved to be an inherently ambiguous. That is any grammar generating this will be ambiguous. Now, you can have a grammar like this, S goes to S1, S goes to S1, S2 sorry, S1 will generate this portion, S2 will generate this portion. Okay. Now, each one of them, this portion S1 will generate this, S2 will generate this. Each one of them can be generated unambiguously. We can generate each one of them in an unambiguous manner. That is, S1 can generate this in unambiguously, S2 can generate this unambiguously. It is not very difficult to see. For S1 I will write the grammar. S1 goes to say AB, A goes to AAB, A goes to AB, B goes to CB, B goes to C. In a similar manner you can write from S2 for generating this, right. So, this is unambiguous, but the ambiguity arises because something like a power n, b power n, c power n, a string of the form a power n, b power n, c power n will have a derivation from S1 and another derivation from S2. So, it will have two derivations, right. So, any string will have either one derivation or two derivations, it will not have more than that. So, what is the degree of ambiguity here? Degree of ambiguity for this grammar, degree of ambiguity can be finite or infinite. Okay. Okay. Now, let us consider this problem. Show that every CFL without epsilon can be generated by a grammar in CNF with additional restrictions. If A goes to BC is a rule, then B is not equal to C. If A goes to BC is a rule, X goes to YB cannot be a rule. Similarly, Z goes to CW cannot be a rule. That is, a Chomsky, a context free grammar is in Chomsky normal form if the rules are of this form or of this form. That is, on the left hand side for any context free grammar you have a single non-terminal, on the right hand side you have two non-terminals or a single terminal. What this says is, if something occurs as the first symbol on the right hand side, it cannot occur on the as a second symbol on the right hand side for any rule. And if something occurs as a second symbol on the right hand side, it cannot occur as the first symbol on the right hand side. That is why you cannot have this equal to this. You cannot have a rule of the form A goes to BB, right. Now, of course, in a particular grammar, given a particular grammar, you look at the rules, keep on replacing one of them. If you have a rule of the form A goes to BB, replace one of the B's as B1 and then proceed and so on. For a particular grammar, it is easy. I mean, there may be say 7 rules or 8 rules, you can do that one by one, you can keep on eliminating. Ultimately, we will be able to do, there is no problem about that. But you have to prove that, right. So, in Greibach normal form, we did that. When we wanted to convert a context free grammar into Greibach normal form, we used two lemmas. We kept on replacing something and then again did some substitution and so on. In a similar manner we can do that, but the problem is In Greibach normal form, when we did that, if you remember what we have done, there were 5 steps. In step 3, you went from A1, A2, A, the non-terminals you arranged them as A1, A2, An. And then in step 3, you went from A1, A2 up to An, and in step 4, you went from An minus 1 up to A1. So, after the step 3, all the An rules will be in Greibach normal form, and when you resubstitute in step 4, all the A rules will become rules in Greibach normal form. A similar manner, unless you do some arrangement and all that, it is difficult to say that the procedure will take, because you may start with the 50 rules or something. When keep on substituting, you may end up with more and more rules, and ultimately you have to prove that somewhere it has to stop. Rather than in this case, there is a simple way to prove it. What you do is, this is a grammar NTPS. Okay. Now, construct a grammar G dash with N dash T P dash, a new symbol S dash, new start symbol S dash. Now, N dash will be, set of non-terminals will be of this form. For each non-terminal, A, you have 2 non-terminals, AL and AR, A left, A right, and one more start symbol. So, when you have a rule of the form A goes to BC in P, okay, in P dash you will have AL goes to BLCR, AR goes to BLCR. You have 2 rules like that. So, this will keep track of the sort of a left hand. See, this way, wherever BL occurs, there will be a rule for BL. Whenever there is a B on the left hand side, there will be a rule for the BL, and you can apply that, right. And whenever there is a rule for C, there will be a rule with CR, and you can apply it for that. But when splitting like this, BR will occur only as a second symbol, BL will occur only as the first symbol. So, there is no question of the first symbol occurring as a second symbol or the second symbol occurring as the first symbol, right. And initially, if S goes to some AB or X goes to, I will use some other symbol, XY belongs to P, start symbol going into something. Instead, you also add, for this you will have SL goes to XLYR, SR goes to XLYR, 2 rules will be there for that. Apart from that, you also have S dash goes to XLYR belongs to P dash. Right. This will make sure that the rules, whatever symbol is occurring as the first symbol on the left hand side will not occur as the second symbol, and whatever is appearing as second symbol will not occur as the first symbol, that is all. Okay. So, let us consider some more problems. Give unambiguous grammar for W. W is a string of A's and B's, and W has an equal number of A's and B's. This example we have considered several times. The grammar which we considered was this: S goes to AB, B goes to B, B goes to BS, B goes to ABB, S goes to BA, not 2, 5, 5, 6, A goes to A, 7, A goes to A, S, 8, A goes to B, 8. We also proved using induction that this generated equal number of A's and B's and nothing else. Okay. The induction hypothesis, we proved that from S, if a string is derived, if and only if it has got equal number of A's and B's. From A, if you derive a string, it will have one more A than it has B's. From B, if you derive a string, it will have one more B than it has A's. And consider this is ambiguous, because if you consider A, B, B, A, B, there are two derivation trees possible. S goes to A, B, then A, B, B, then this one you can have as B goes to B, S, S goes to A, B, no, S goes to B, A goes to A, B goes to B. This is one derivation tree. Another one will be S goes to A, B, A, B, B, this will go to B, this is goes to B, S, A, B. So, A, B, B, A, B will be generated in two different ways. So, this is an ambiguous grammar. We want to give an unambiguous grammar for the language. The reason for this is, at this stage you have the sentential form BB, and from these two BBs you have to derive this. From a B you can derive a string which has got one more B than it has S, isn't it? So, this you can either split it as B, BA, B, which will give rise to this derivation tree, or you can split it as BBA, B, which will give rise to this derivation tree. That is why the ambiguity comes. And in the proof, while proving this, we proved it by induction, but also for another example, if you denote number of A's minus number of B's and the length of the string here, and take any string, suppose it is A, the same string A, B, B, A, B. The number of A's minus B's as you go along the string will be A, B, B, A, B. Because the number of B's is equal to the number of A's, it will start at the origin and it will touch the x axis in the end. In between there are several possibilities. The diagram may just be like this, or it can be like this, or you may have something and then something, or this portion even may go below this. To have unambiguity, you have to change. So, there is no hard and fast rule how you find the unambiguous grammar. You have to just think and see how it can be done, that is all. Because it is undesirable to find out whether a given grammar is ambiguous or not. Okay. And depending upon the structure of the sentences, depending upon the language you are given, you have to look into that and see how it can be generated unambiguously. Is it possible or not? Here, the first rules if you change, S goes to ABS, and S goes to BAS. Let us take the same string AA, BB, AB, start from S. You apply the rule AB, S. Actually, the idea is like this. Suppose this number of A minus number of B is this, then if the graph is like this, it may have ups and downs like this. The first time it touches the x axis, this portion will have equal number of A's and B's, and because of that this portion also will have equal number of A's and B's. So, the idea is use the first two rules. If it touches the x axis in the middle, the first portion you try to generate this, and recursively it may again, the graph may go like this. Then, so this portion will be generated by the this S again you can repeatedly apply. If you do that, it has to be done. Since AA, BB, the first time this portion has equal number of A's and B's, and the other portion AB also has equal number of A's. So, from this S you should be able to derive this AB, from this portion you should be able to derive this. If you do this, any string can be derived only in one possible way. Now, let us, it is slightly different from the example, other example. You can show that this is always ambiguous. How do you show that? Yes, A, suppose I will take an example rather than, suppose W is A, B, B, some string. The rules are S goes to W, S, S, S goes to A, S goes to B. So, you can always have something which can be derived in two different ways in this case. How is that possible? A, I will put W, W, S, S, and then S can go to A or B. Again you can have another W, S, S. Now, three symbols can be derived from that. Another way of doing it will be S goes to W, S, S, W, S, S, W, S, S, W, S, S, W, S, S. I have taken W to be A, B, B. So, here you can make it go to A, B, B, A, B, B. In a similar manner, if you do W, S, S, make it go to A, B, B, W, S, S, W, S, S, A, B, B. This will go to A, B, B. How many times you get A, B, B? 1, 2, 3, 4, 5, 6, 7 times you get. This is W power 7. How many times you get W here? 1, 2, 3, 4, 5, 6, 7. So, this also generates W power 7. In general, if you take some W, then consider length of W to to be n, if you consider the length of W to be n, take W power 2n plus 1. In one way you can derive like S goes to WSS, WSS and so on, and finally these S's should contribute to 2 W's. Here you will generate n minus 1, 2n minus 1 W's, and this will generate 2n symbols, that is 2 W's, we can generate them. In another manner, from S goes to WSS, you can generate again from this n symbols and n minus 1 W's. So, 1 W will be n minus 1 W's here, and here again n minus 1 W's, and with the S's 1 more W. So, totally the number of W's will be generated is 1 plus n minus 1 plus 1 plus n minus 1 plus 1, this is 2n plus 1. The string generated will be of the form W power 2n plus 1. If you take such a string, it is always possible to derive in 2 different ways. So, such a grammar will always be ambiguous, whatever may be W. But if the length is 2 or more, you take W power 2n plus 1. If it is single letter, for example, if you take a single letter, S goes to ASS, S goes to A, S goes to B. Here again you will have ambiguity, but the string you have to be careful. ASS, ASS, then whatever you generate another string S, A, S, S. Now, to generate this you will have another A, S, S in 2 different ways. You have to show A, S, S, right. Then these symbols can go to different symbols and so on. So, minimum length 7 you have to take, right. Now, again A, S, S, you have to use this rule, right. So, this has to go to A and this has to go to A. These 3 you can make it go to A or B, right. Suppose I make it go to B, 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 B. So, I had the minimum length I have to consider is length 7. So, that it is not A power 2n plus 1, we are not considering A power 5, right. In a similar manner, the same sort of argument you can use for proving this. S goes to ASS, BSS. This will also be always ambiguous. Next, we will consider this problem. Let L be a regular set, then half of L is defined as x, xy belongs to L, length of x is equal to length of y. Of course, you can consider an alphabet sigma over an alphabet sigma. What it really means is, from L you take all strings of even length. Take all strings of even length, and in each string you consider the middle one, I am sorry, the first half only, then such strings will form a regular set. Half of L is, you have to show that half L is regular. How do you prove this? In fact, like that you can prove 1/3 L is regular and so on. I mean, you can define like that. What will be 1/3 L in that case? You can also define 1/3 L. X, x, y, z belongs to L. Length of x is equal to length of y is equal to length of z. That is from L you take strings of length 3 and you just pick up strings of which are multiples of length 3, I mean the length of the strings is a multiple of 3. Then from each of such strings you take the first 1/3 portion alone. Such strings will form a regular set. As a simple example, look at AB star. Half of L accepted by this machine, I am not marking the dead state. AB, 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 okay. So, if you take strings of even length and take the first half, what will you get? If you take AB, you will get only A. If you get AB, AB, you will get AB. If you get AB, 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 you will get ABA. If you get AB, 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 AB 4 times, you will get AB, AB twice. So, half this is L, half of L will be AB star plus, I mean can be represented by this regular expression. Epsilon will also be there. You can have AB, you can have epsilon, you can have A, you can have AB, you can have ABA, you can have ABAB, you can have ABABA and so on. This is a regular set. To show as an example, and this will hold for every regular set. And how can you prove that? How can you prove that half of L is regular? So, we have to show that half L is regular. How do you prove that? This is what we want to show. You construct M dash, K dash, sigma, delta dash, Q naught dash, F dash. Construct a machine M dash is equal to this to accept half of L. Right? Where L is accepted by M is equal to K sigma delta Q naught. Now, I will not write down step by step, I will give the construction, generally construction and then illustrate with the example. The K dash, the set of states K dash, they will be of the form, they will be, okay. Suppose K has n states, it has got n states, Q naught, Q1, Qn minus 1. You have to have some order where this is the initial state, any of them can be final state. suppose K has n states, then a state in K dash will be a n plus 1 tuple. You take the state in K dash as a n plus 1 tuple. The first one will be a state, this will belong to K. The second, third up to the other one, they will all be sets, subsets of K. The first one will be a single state, the remaining n are subsets of K, right, and the initial state will be Q naught, Q0, Q1, they are all subsets are singletons. This will be the initial state, right. The initial state will be like this. How do you define the mappings? I have a state is of the form Q comma S1 comma S, I will put it as S naught rather, S naught S1, Sn minus 1. The state will be of this form, right, where Q is a single state, S naught, S1, S2, Sn minus 1 are subsets of states from K. And how do you define delta dash this A, where A is a symbol? This you define as, the first one will be delta of QA. From Q, if you read A, you go to say state P, say, which is represented by delta of QA, you go to that state. And here you will go to say T0, T1, Tn minus 1, they will be subsets. How are these subsets defined? From any one of the states in S naught, if you get a symbol, any symbol, not necessarily A, by a single move, single transition, what are the states to which you can go? From any one of them, by reading one symbol, it can be A, B, anything. What are the sets of states to which you can go? That is given by T0. And S1 represents a set. From S1, by one move, that is by reading one symbol, what are the set of states to which you can go? That is T1. So, you can define the mappings like this. And what are the final states? Final states are of the form some Qi, then say R0, R1, these are all subsets, Ri, Rn minus 1. If Ri contains a state from F, this will be a final state. This belongs to F dash, or this is a final state if Ri contains a state from F. What does that mean? Starting from this initial state, this is the initial state. So, starting from this, if you reach a final state, what does that mean? After reading some portion you have reached Qi, and from Qi, after reading the same number of symbols, you have reached the final state in the original automaton. If you reach a final state like that in this automaton starting from this initial state, that means starting from q naught after reading the original machine, starting from q naught after reading some x, you have reached qi, and because Ri contains a final state, starting from qi after reading a string of equal length, you have reached a final state. So, from qi after reading some string, you have reached a final state here, but the number of moves is the same. What number of moves you are making from here to here, each time you are also counting just the one transition, right. So, the number of symbols you have read from going to qf is the same as the number of symbols you have read from q naught to q1. So, this automaton will accept half of f. This is a general construction. The same sort of an idea I can use for 1/3 L, 1/4 L, 1/nth L and so on. Okay.